Right, okay, so good morning. So I hope that's all clear and everyone can hear me, and sorry for starting about a minute late or so. Okay, so at the end of the last lecture, let me just get rid of me. So at the end of the last lecture, we were looking at a Sallen key network. Let's go back a bit. So we're looking at this type of network here, this one here, and we did some analysis of it and tried to massage it into the shape of a second order filter, and showed that we could do that, and it was a lot of combinations of R's and C's gave us the equivalent of this of omega naught and Q in this second order template. So we looked at ways of constraining this, because there's a lot of combinations of R1, R2, C1 and C2 that might work. It looked a bit complicated. So we took this approximation of making R1 equals R2 and C1 equals C2 and just then called that R and C. And then we can boil the omega naught down to 1 over RC, and Q is defined by the amplification of the amplifier in the circuit. Which gives us independent control of both interesting parts of this second order system. We started thinking of other constraints, and we started to think of more sort of commercial constraints. Cost is always an issue in electronics, and having a gain in our amplifier that's not 1, i.e. not a buffer, means that we have a extra couple of components, which takes up more space and is more cost, and there's more tolerances to worry about as well. So if we make A equals 1, we can get rid of 2 resistors and just make the amplifier into a voltage follower circuit. And if we do that but keep our constraints that R1 and R2 and C1 and C2 are the same, we then only end up with a Q of 0.5, which is what this is purporting to show down here. So if we make R1 equal R2 and C1 equal C2, and we make A equal to 1, we end up with a Q factor of 0.5 or so. So what we can actually do is we've still got control over the omega naught and the Q by looking at the R1s and the R's and the C's. And if we don't constrain them to be identical to each other, that may be the way forward. So what we've got to do is think of some more constraints to allow us to vary this Q, even if the gain is 1. Right, so if we start to just make the substitutions back into the standard equation and see what's going on, you can see that C1 only appears in the S squared term. Not appearing in this term over here, so we've got something that we can alter over here that will affect this but won't affect this. So if we fix this first, we may be in the chance of then adjusting this independently. It's still a bit tricky, but you can sort of do that. And one way of doing this is to pair the components up and give a relationship between their values. So if we make R1, instead of making R1 equal to R2, we just make it a multiplication factor of R2. And do the same for the capacitance, but have a different number, so in this case N. So R1 equals MR, R2 equals R, so they're just related by this factor M, and these are related by this factor N. You can then put it into the equations and end up with Q factors and omega naughts that are affected by RC and this relationship Mn, and Q is only affected by Mn. And once you actually then include Q and omega naught to give us our damping factor, so 2 zeta over omega naught here, or 1 over omega naught Q, you can see that the N disappears from this part of the equation, but N is still in this part. So again, we can we can mess about with this part, and then when we've got that happy, we can then calculate an N accordingly to adjust this. It's still a bit fiddly, but it does give us independent control. So we pay for complexity in design with simplicity in circuit, and therefore reduce costs. And that's what people will pay you the big money for, because they only got to pay you once. They can make millions of these circuits and save a few pence each time. So it's possible then to get independent Q and omega values, but it does require a careful choice of capacitors and resistors, and it also requires you to dig into the equations a bit and understand what it is that the equations are representing and what you can tweak and what you can't. So that's it. With a bit of knowledge of what's going on, there's a chance that you can actually come up with some imaginative solutions to doing what you want. So that was the Sallen key. We move on now to look at something called a Rausch filter, which looks remarkably similar, but is subtly different in certain ways. And there are some disadvantages to the Sallen key filter, some of which are significant and others are less so, depending on what you want to do. But nowadays, low voltage is where everything's at. We no longer tend to operate op-amp circuits on plus and minus 15 volts. We want to operate them on 0 to 5 volts, 0 to 3 volts, 0 to anything low for low power systems. So we have to think about that. And we've seen with op-amps there are some issues with common mode and also rail-to-rail operation. So the Sallen key falls foul of some of those issues. In the Sallen key circuit, for example, you can see here that the common mode voltage here is not constrained. It depends on the output voltage, and for a certain extent on the input voltage. So the common mode signal here, although both these are going to be the same, if there's a common mode signal, could be going up and down depending on what the signal is that's coming in. And we've seen that common mode can be an issue in amplifier circuits. We also have issues maybe with these op-amps not operating near the rail or not operating near the power supply rails. So we have to consider what's going on here. So we can probably get away, or we need to think of a way of getting away with a single rail operating op-amp. But if we're clever, we can just use one that only goes down to the negative rail, and we can accept a little bit of problems in the upper rail. Anyway, so these are things that you need to think about in the structure. So the Sallen key is not ideal from that respect. If you've only got small signals that are centered around a certain value, then it's probably fine. But for more general purposes, you might find that under certain conditions the common mode becomes a bit of an issue. The issue, it's maybe not such a significant issue, and it's quite subtle as well. It's not suitable for digital tuning, as key capacitor has the signal at both ends. So this capacitance here doesn't have an end at ground, which means that if you wanted to put a capacitor in parallel with it and switch it in using an analog switch, then the switching voltage of analog switches tend to be related to the input voltage. So you need to make sure your switching voltage is significantly above the signal voltages, which may not be the case in this case if you're not referenced to ground at one end. So it's going to be tricky to include a digital switch in this loop here. So that's one thing to think about. It's not a real significant problem, but you never know. One day you might find yourself in a position where it becomes an issue. Okay, what else was it? Okay, so the Rausch filter is a way of getting around some of these issues, and it says it can also be constructed in fully differential form. So we understand from now that differential circuits are quite important for getting rid of common mode noise, and particularly in communication systems a lot of things are differential, and in fact FPGAs now have a lot of differential only inputs so that they can get very high speed throughput for noisy communication signals. So this is not significant. This is just an example of a differential structure to show that you've got the more perfect your symmetry from plus to minus, the better the performance of the circuit is going to be. And obviously everything here is referenced to ground, so there's no common mode issues. Anyway, so the Rausch filter looks like this. It looks, fairly similar to the Sallen key, but it's different. And if you look at the two, you can spot the difference, and that's left for homework. If we want to analyze this, we can do it by standard node analysis because it's a nice linear system. So you do a node analysis at Vx for here, and this will be so this expression here relates to this resistor here. This one here relates to this part of the node, this bit for this bit, and this bit for this bit here. So because it's a node, everything has to work the naught, so we do that, and then to get a link to the output we have to look at this node as well. And so if we look at that node, we can do exactly the same thing and end up with an expression that we can then substitute for Vx in this one, and that will allow us to again get an expression for V out over V in. Okay, where V1 happens to be V in. So if you take those, you substitute for Vx equals V out over SCR into here for everywhere you see a Vx, and then you mess around with the equations, you end up with something like this. And again, we're trying to massage this into the standard form of s squared plus s plus some constant. And you can see that we can do that, but there's a lot of writing involved and a lot of subscripts, and can be very easy if you start to do these by hand to get your R1s, R2s and R3s all muddled up, particularly if your handwriting is as messy as mine is and you can't tell the difference between a 2 and a 3. So again, once we start comparing this with our second order template, we can start to see that we've got a gain term, which we know from filtering is not significant because it changes the scale of everything, a frequency independent term. We've got an expression for omega naught, which comes from the template over here, and we've got omega naught over C, omega naught over Q rather, which comes from the coefficient of S. And so with a bit of manipulation you can work all this through, and again, if you start to put some constraints in because you've got too many resistors to worry about here. So for unity gain at DC, we've got to start somewhere, so let's just let R1 equal R2 so that this factor here becomes 1, and that just gives us a gain of 1, so that sort of normalizes it. So there's a constraint. Why don't we just allow R3 to be equal to R as well, just to see what happens. And if we do that, suddenly we find that we end up with Q is equal to something very simple in terms of just the two capacitances. Omega naught is also dependent on the two capacitances, and the gain becomes 1. So it becomes quite neat in that respect for a fully normalized design. So the normal template that you would look at for this then, it still has the resistances in there obviously, just because they're not significant in equations means that you still need them though, and the relationship between the capacitances and the resistors is defined here. And we will change the resistances when we do the impedance scaling or the frequency scaling. Remember, this is for a normal template. But we can start with this and we end up with a very simple relationship between these two capacitances, that we've got 3Q over here, whatever the Q factor is, and we've got 1 over 3Q here with normalized resistances in between. So it's actually quite elegant from that respect. So that's quite a neat system. So one of the other things we need to arm ourselves with is how to convert from a low pass filter to a high pass filter. We've concentrated so far and done some detail for Butterworth and 2 different sorts of construction, so Salenky and Rausch, but only for low pass. So we've only looked at a low pass system response. But the nice thing about this is that we once we've got our low pass prototype, we can then apply some transformations to that solution to give us all kinds of other types of filter, and the transformation is quite simple. So again, we just have to learn all the rules for low pass for getting what we want, and then we can convert it to high pass or band pass or whatever we like, just by doing some transformations, simple transformations in the maths that we've just solved. So in order to make a low pass filter into a high pass filter, we just replace S over omega naught with omega naught over S, and then do the maths to work out where our poles and things are. And if we want to make a band pass filter, someone else has done all the work and has told us that we can replace our S over omega naught in our template with S over omega naught squared plus 1 over S over omega naught. So that obviously makes the maths a bit more complicated, but the principle is the same. But we have doubled the order of the filter because we've introduced an S squared term over here. So we've gone from S to S squared straight away. So that doubles the order of the filter. So it makes the circuitry a bit more complicated as well. So as an example, let's consider a second order Butterworth filter, which we've done earlier. Our low pass prototype is given by this with our effectively our 1 over root 2 type damping factor in there. So that's what we solved for our second order Butterworth, which is a sort of quite trivial solution in terms of a second order system. So the high pass system then just becomes omega naught over s. So we swap this s over omega naught for omega naught over s, and this one for this one. And then we can do a bit more manipulation again, and then we get this back into a form where we've got s over omega naught squared on the bottom, but we've now got a term on the top that's slightly different. And this will have the same cutoff frequency as the low pass, and it performs accordingly. So it's just the sort of the mirror image in some ways. It's we'll see in a minute when we plot the characteristics what I mean by that. And the nice thing about the Butterworth filter is that once you've defined, this is a sort of shortcut, once you've designed a low pass filter, if you want the high pass filter, all you do is you swap the R's and the C's around, and we'll see what that actually means. You can't do that other types of filter, unfortunately, but you can with the Butterworth. Right, so if we wish to design a high pass Butterworth filter with a cutoff frequency of 1 kHz, let's start with our low pass prototype, which is this one here, and the standard transfer function for that is given by this, so we should be getting familiar with seeing this now. And for the second order Butterworth, we can go back to that table and pull out the second order Butterworth polynomial, which is a trivial one in some ways. So it's just s squared plus root 2s plus 1. We will plan to use our Sallen key solution for an example, and we will also allow ourselves to vary a, which means that we can say that R1 equals R2 and C1 equals C2, and we have a to help us play with the Q factor. So if we go back a few slides and have a look, we can see that omega naught is given to us by 1 over RC, and Q is given to us by 3 minus A, whatever the gain of the amplifier. Well, we define what that is, and then we design the gain accordingly. So all we've got to do is start putting some numbers into here to work out what we need for these, if we know what these are. So for a cutoff frequency of 1 kHz, for example, omega is going to equal 2 pi f, which is 6283 radians per second. So that's what we're aiming for in terms of frequency. We know that we've got a Q of 0.707, having looked at the standard equation, because it's omega 2 zeta is omega naught over Q. So we know we've got a Q of 0.707 that we're looking for, so we can work out A from that. 3 minus 1 over Q, Q is 0.77, 3 over 1.414, which gives us this number of 1.586. So we need this gain of this part of the amplifier, this non-inverting amplifier, to be 1.586, and we have to know the gain is given by A plus 1 plus the ratio of the two feedback resistors, and so we can then solve to give us a ratio of RF over RG. Then we have to pick a value of one of them, so let's say RF equals 10k, work that back through, and RG equals 17.1k. And this is where the problem might arise, getting a 17.1k resistor. It's not a standard resistor, so there may have to be a bit of messing about with the ratio of these values to try and get these as close to standard ones as you can. Otherwise you end up fitting a potentiometer to get this well matched. And this comes back to the problem, if you want a high Q, you have to control A very well, and controlling A is the ratio of two resistors, so we have to control those resistors very well. So we're then free to choose values for R and C to give us our omega of 1 kHz or 6.283 radians per second. We just apply the equation in this case, omega naught equals 1 over RC. We've got R and we've got C. We've got to pick one. So let's say C is 100 nanofarads as a test, and then it's simple enough to rearrange that to get R equals 1591 ohms. So that's it. We then put in our values, and so 1591 for these resistances, they were the same, 100 nanofarads for this one. The gain for the gain of the amplifier ratio was 10k to 17.1, and both capacitances are the same. And then if we simulate that in our simulator, we can see that we've got a response that is flat and then starts to fall away, and at 1 kilohertz, if we measured that properly, we'd find we were about 3 dBs down. So in this case it would be about 1 dB. So that all works very nicely. Very good. So to turn this into the high pass filter, because it's a Butterworth, we just swap the R's and the C's around. So here's some R's and there are the C's, and now we just put some C's here and some R's here. Same gain, same everything else, and we simulate that and we end up with exactly the same response, but mirrored, if you like, so mirrored around some factor here. And this is 1 kilohertz. Again, we're going to be 3 dBs down at 1 kilohertz, and then above that it's going to allow signals to pass through. And if we plot both responses, you can see where the mirroring comes, and at 3 dBs down is where these cross at 1 kilohertz. So everything works really nicely. Okay. So again, just a little bit of knowledge of what the equations mean, and some knowledge of the circuitry and what you're trying to achieve allows you to get to these designs and be quite imaginative about it. So try the same with the Rausch filter. Again, we've got the same polynomial and the same values of omega naught and Q that we're aiming for, but there are different relationships in the circuitry to allow us to calculate these things. So again, cutoff frequency is 1 kilohertz or so, so that's the equivalent of 6283 radians per second, so that's the same as before. Again, we're looking for a Q of 0.707 for a second order Butterworth, so that gives us C1 equals 3 times Q. We know what Q is, it's 0.707, so we can work that through, and that gives us 2.121, and therefore C2 is going to equal 1 over 3Q, which gives us 0.471. All the values of R are 1, so we now just frequency scale to give us a cutoff of 1 kilohertz. So it becomes actually a very straightforward process in that respect. So we divide the capacitances by the frequency. So C1 becomes 337 microfarads, C2 becomes 75 microfarads. We then impedance scale to get R to be a sensible value. So we just multiply R by 1K, and then we divide capacitances by 1,000, and so they just lose, they go from a mu to an N in that case. In the case of a high pass filter, we can swap the R's and the C's, make the C equal 1 then. So that's the difference in the process becomes that where we made R1 in the prototype for low pass, in this case we make C equal 1, and then we make the resistors 3Q on 1 over 3Q, and they got the same ratio. Again, we then do the frequency scaling, because our prototype was for a frequency of 1. We want a frequency of 1 kilohertz, so we have to apply some frequency scaling, and then we have to apply impedance scaling as well to get our 1K. And that leaves us with these numbers. We follow it through, we end up then with both implementations on this circuit diagram here. So we've got a low pass and a high pass implemented using the values that we've just calculated. We calculate those values, and once again you can see that we got 1 kilohertz cutoff frequency with 3 dBs down, and in the case of the Rausch filter we've actually got a unity gain. On the case of the Sallen-Key we actually had a gain of I think it was about 4 dBs or so. So it's a straightforward process. We've rushed through it a bit there because we're short of time on this module, but if you look on the ECS notes page, there's some examples of filters and some sort of a couple of questions that you can try for designing filters, so you can go and try that out and follow these notes through if you didn't quite follow exactly where the Q's and the omegas and things came from. So if you spend half an hour or so revising these slides and then looking at the examples on the notes page, hopefully you'll get a very good idea of how to design it, and it'll allow you to design a filter there as well. So I think it's fourth order one we designed there just to make it interesting. So you just have to remember that a fourth order filter will be just 2 second order stages cascaded, so you get to do the calculations twice, just for some practice. Okay, so quick summary of what a low pass and a high pass filter looks like in both of these common architectures. So we've got the Sallen-Key network with the different values of resistances there, and we can work out what we're going on down here, how to get from low pass filter to high pass filter in both cases. But it's once you've done it a couple of times, it does become very easy. So what I would say is just try and design some arbitrary filters. Say you want to pick one that has a cutoff frequency of say 3 kilohertz or something. Try and design one that does that, put it in the simulator and just check it all works properly, and then design a high pass filter, put it in the simulator and check it all through. There's really no replacement for just doing a couple of these things, and the reality is that with simulators now you can come up with as many different designs as you want for cutoff frequencies and check it yourself, so you don't particularly need worked examples from that respect. What you do need is a method, and the methods are in the slides. Right, so Butterworths are very common and very popular, have a nice flat frequency response, and are easy to design in many ways. We may want to make some compromises to try and emphasize some features of our filter over other features, and one common example of this is something called a Chebyshev filter, and this uses, unsurprisingly, a different polynomial to the Butterworth polynomial. It uses a Chebyshev polynomial, which no one has ever heard of, or they've heard of it but no one knows what it is. So we'll just introduce what it actually is, and that's about as far as we'll go with that. The nice thing about the Chebyshev polynomial or Chebyshev function is that you actually have an initial faster rate of cutoff, but at the expense of an amplitude ripple in the passband. So what does that mean? So here's the response for a Butterworth filter, which is nice and smooth and running away. The Chebyshev response has some variation in what we would term the passband, a bit of wobble, particularly at these higher frequencies, but it's controlled, and then this cutoff frequency here is very sharp before it starts to then revert to the however many dBs per decade for the order of the filter. So if it's a second order Chebyshev, it'll be 20 dBs. This one's a fourth order, so the overall decay rate here is going to be 80 dBs per decade. So the Chebyshev, although it has an initial rate that's higher, eventually trends towards 80 dBs per decade. So this is the log-log plot showing you what's going on. So they look similar, don't they? Really, it's got a bit of wobble here, but it doesn't look too problematic. And you've got a nice sharp response here, but then it's not a million miles away. If you look at it on a linear scale, so the same one, you can start to see where the issues may be. So this is the same response but on a linear scale, so you can see that actually the wobble in the passband is quite significant, but you can also see that the cutoff is very, very sharp despite it only being a fourth order filter, and it's only at these frequencies that it starts to then match the response of the other system. So in the sort of linear world, if you like, for this response here, you can see that you get a very, very sharp response, and you can see that that's actually quite a nice response. So if we can live with this amount of wobble in the passband, you can see that you've got a good cutoff. So you've got nice sharp demarcation even for a low order filter, and you might not get that from this sort of bode plot here. You might look at that and go, okay, well, it's quite close. But if you look at it in the linear domain, you can say, well, actually, where it all matters, it's all very significant. So this is a good example, I think, of just being aware of the differences between bode plots, which are good for analysis, and linear plots, which maybe just give you a bit more of an insight into what it really looks like in the real world. Excuse me. Right. So it is immediately apparent that the bode plot hides a multitude of sins. So we've gone to that. Just be aware that both ways of displaying the response can give you insights into different aspects of what you're interested in. So we can still use circuit architectures that implement second order functions, same as we did before. It's just that the solutions to the equation, or the second order equations, will be slightly different, which means that the poles, we've only got two poles, the poles will be in slightly different places, and they'll be conjugate anyway. So we can use exactly the same circuit architecture, it's just we need to change the values around a little bit. And unfortunately the design rules for a Chebyshev filter are more involved than for Butterworth. Therefore it says inevitably the derivation of the function is also complicated, although it runs in the same general pattern as for the Butterworth derivation. So we're going to quickly, for those of you who are interested at least, run through the main points of the Chebyshev derivation, but I'm not going to labour on it too much because well, you don't have to really. People have done all the calculations for you, so you end up looking things up in a book, but it's well worth just understanding the nature of the path through, and don't worry too much about understanding it. There's no way that I'm going to include the derivation of these equations in an exam. It's just really not worth it. So sit back and relax on that one for a bit. So once again we start with the square of the magnitude, because we want to do this trick of getting rid of half the poles. So we start with hs squared magnitude, and we set that equal to this function here, which includes the Chebyshev polynomial Cn here, and Cn is defined as Cn of omega is cos of n, whatever n might be, just a constant, and the inverse cos, or anti-cos if you like, arc cos of omega itself. So why he came up with this, I don't know. What it, where it came from, I don't really know. But it's just happens to be a very useful function in terms of defining filters. So it says here, this on the face of it isn't much help, until we realise or prove, if you're mathematically inclined, that it satisfies the recursion formula, which is where it starts to get interesting, of whatever order of polynomial, so n plus 1, one up from the one you're interested in, is defined as 2 omega times the Chebyshev of the previous order polynomial and minus the previous polynomial to that. So we've got some kind of recursion. So we've got n minus 1, n plus 1, and as we increase n we will start to get our higher order functions. So this allows us to generate functions that are obviously polynomials. So in fact, once we have two consecutive polynomials, we can calculate the rest using the recursion formula above. So the first two are simply 0 order is put these numbers in, we get 1. Put first order in and follow that through, it becomes this function here, omega, and then when we've got those we can start to then throw them into this equation and we can generate as many orders as we like going forward, because these are actually relatively straightforward outputs. So we just have to accept that that's the definition. I don't know where it comes from, but we don't need to. So it sort of depends what they look like, really. So we can generate, you can see they start to get quite complicated as we go up in order. And so using a third order as an example, we can plot that and we can show that this has a ripple of plus and minus 1 if we plotted it like that. And this is the ripple, if we like, so the peak of the difference in the turning points. And if anyone wants to look this up, I got it from this book here, Circuit Analysis Simulation Design. It's quite a good book actually, but I've taken out the relevant bits for you here. There are a couple of mistakes in there though. So if we want to start to make this into what looks like a filter response, we can start to manipulate it. So this is, we've taken the basic polynomial and we said, well, eventually this is going to be a ripple in our amplitude response, and we don't really want ripple, or at least we want to know what it is. So we'll define the ripple as epsilon, and then just plot epsilon times the function. So obviously you're just going to, as epsilon gets smaller, this ripple function will get smaller. We've got the negative solutions in here, or down here at least. So if we square this, so we take this function and we just square it up, and that flips everything up on its end. So we end up with this type of response now. Squaring it means there's no negative response anymore, but we've actually got epsilon squared as our peak ripple. So you can sort of see how we're constructing what we were interested in our response. We then just add 1 to it to offset it away from 0, because we don't want to invert 0 because that becomes a big number. So this is just for mathematical convenience. So we just say 1 plus epsilon blah blah blah, and that plot that, and it looks like that. And then if we do 1 over that function there, we end up with this type of response, which you can see if we took half of it, looks like a filter response that we're interested in. So that's how we've sort of constructed the response from the Chebyshev polynomial, and this is what we're interested in terms of implementing in our circuit here as frequency increases. Okay, so that allows us to understand at least why this polynomial is important, and how we've actually constructed this response from it. But we've still got to work out where the poles and things are in this to understand what's going on, and have a chance to actually then implement it in the form of a circuit. So remember, this is still the magnitude squared. It still includes poles in the positive half. So we do the same trick as we did in the Butterworth filter, to only take half the poles. So we've only got the poles in the left hand side of the Argand diagram, which are the stable ones, and that gives us a magnitude response, because it's not squared anymore, of 1 over the square root of that, and we can just take half the poles because they're all equally spaced. So we get the transfer function. We now have to extract its poles, and this is obviously going to be harder than for the Butterworth. If you remember, the Butterworth filter had all its poles on a circle. So geometrically that's quite easy, and actually then you can work it out by hand by just dividing the circle into the right number of poles and reading off the angles, turning that into a complex number, and then just working out where the position of the pole is from that. In the case of the Chebyshev function, because we've got this epsilon factor, the poles are actually on the locus of an ellipse and not a circle. And the ellipse becomes something that is obviously squashable. We can spread it out, make a very thin one or a long one, depending on the value of epsilon. And so that we've got another degree of freedom compared with what we had with the Butterworth, because everything was on a circle with the Butterworth. And the nice thing about the Butterworth as well was the radius of the circle was actually omega naught. So all the poles on a Butterworth, when they're on the circles, this is Chebyshev, so I'm running the risk of confusing people here, that these radiuses where the poles were always the same, and they're actually omega naught. Because all the poles are on their own different radiuses now, because the ellipse has, its radius is constantly changing as we go around it. We don't really have this concept of omega naught anymore, because each pole has a different value of its frequency, or its turning frequency, cutoff frequency. So that starts to become a bit of an issue and does complicate things a little bit. But if we understand that's what we're doing, we just each pole will have its own different omega related to it. So we don't really have this concept of omega naught anymore. Then we can maybe move ahead with that. It's actually not as bad as it sounds. So in order to get the poles of the Chebyshev function, we need to solve this, and we need to define E, omega, and n. So this W is an omega from here. Yeah. So we need the order, we need the amount of, this E is epsilon, we need the amount of ripple we're prepared to accept, and we also need a valid order of the filter. So to start making that a bit more practical, so we need to move back from the filter response to these mathematical definitions. So we want something that we're interested in. So we can define epsilon in terms of this thing called delta, which is delta squared becomes the value of the bottom of the ripple band that we want if we draw this out. So from 0 up, it's related to the amount of attenuation we're prepared to accept. And that's related to this value of epsilon squared by this kind of relationship, which you can get just by sitting down with a bit of paper and having a look at the definitions. So delta, which is the thing that is a design parameter that we're interested in, leads us to a value of epsilon, which is a mathematical feature of this equation which we need to solve for. So we're going from practical real world to abstract mathematical world, and the delta is something we can measure, epsilon is something we need. So we can then define the ripple in terms of dBs, which is what we like to do. So our dB becomes the equivalent of 1 minus delta, which is the equivalent of that there. And therefore, we end up, and the whole point of this exercise is to get to a point where we can define epsilon in terms of some dB value that we can define as an electrical specification. And that allows us then to calculate E for a specified circuit parameter of RdB. So we can now, in principle, solve the Chebyshev polynomial assuming we give a value to n, the order of the filter, and we know the cutoff frequency. So these are things that we sort of expected and know. But actually, these are design functions as well that we can work out from sketching the desired frequency response and working out what we need. So, but sometimes it's not enough just to say I want a certain cutoff frequency. You might be actually more interested in saying I want a particular gain or particular attenuation at a certain frequency in the stop band. So what we mean by that. So what we might be saying is that we've got a signal here. So this is frequency and this is amplitude, and we've got another frequency here. I don't know why it's put that line there. And what we want to do is we want to allow this one through, but we want to reduce this one to a certain value. We need to have attenuated this by a fixed value. So we've got our frequency response does that. So we're interested in what's the value of the gain at this point here. And as long as our signal is reduced by this factor down here at this point, that's what we're interested in. And if we know that, we can then maybe work back through to work out what order of filter we actually need and what cutoff frequency we need to still allow this one through. So instead of saying I've got this cutoff frequency here and I've got this order here, I'm hoping for the best that this will be down at the right frequency, we can go the other way and say we need to know what the attenuation at this frequency is, what order of filter do we need to achieve that, and what cutoff frequency can we get away with. So that's all that meant. So that's just a question of then solving the Chebyshev polynomial for a given value of attenuation at a fixed frequency and working out what polynomial will give us that, given that we've given it a value of n. To do this, we need to solve the transfer function for omega is bigger than 1, because omega equals 1 is our cutoff frequency. And we can't do that because this definition of the Chebyshev function won't allow us to solve that for omega is greater than 1. But some other people have done some sums, and we need and they've come up with an alternative definition for the Chebyshev polynomial for omega is bigger than 1. So anything above the cutoff frequency, if we want to solve it up here somewhere. And it's this with hyperbolic cosine functions in it. So again, we don't need to worry particularly about where it's come from. We just need to know this exists, because this allows us to then solve our equations going forward. So you can rewrite the transfer function using this new definition of Koch, and then we can solve this for n, because we want to know the order of the filter, given we know what the required attenuation in this stop band is at this given frequency here. Okay, so we've got a known frequency and we've got a known attenuation, and we've got the amplitude response, which is the red line for the whole thing. And given we know the equation and we know this frequency because we've said we want it to be this frequency, and we know this amount of attenuation because we've defined that. That allows us to then rearrange this to give us n. So we can calculate the order of the filter we need for that. And if you do the sums, n becomes this function here, and allows us to define an amplitude at some given point for a given system. So by defining a gamma in the stop band at a frequency omega and defining a ripple in the pass band, we can calculate the minimum order of the filter required to achieve that design response there. Right, so we've whipped through that. It's probably very confusing. You need to go through that slower and look at the filter example designs on the notes page. I think we're going to do a Chebyshev design example next anyway, but it wouldn't hurt for you to start looking at the examples on the notes page and just see if you can understand the method of the calculation. There's no substitute for just designing a few of these, as I said earlier, and then it sort of becomes obvious what we're doing. It's quite subtle in places. If you're mathematically minded, it's going to be really obvious. If you're not mathematically minded, you're going to have to work at it a bit. But if you just do it for a couple of examples, you'll get the idea, and then you'll understand where the shortcuts lie. Right, so I'll stop at that point because I'm sure you're overwhelmed with that, and we'll pick this up again next week, and you've got the weekend to go and have a look at the notes and maybe do an example or two.